Have you ever had one of those moments, an aha moment, where suddenly a piece of the universe just clicks into place?
Yeah, those moments that make everything feel a little clearer.
Exactly. Well, today we're diving into one of the biggest ones in modern science, the discovery of the J-particle. It's this incredible story. Earned Samuel C. Ting the Nobel Prize in '76. And it fundamentally changed how we see matter.
It really did. And Ting's own account, especially his Nobel Lecture, it's not just science. It's like an adventure story, weaving together history, theory, and this just monumental experimental effort.
Right. So our mission today isn't just what they found, but how. The ingenuity, the enormous challenges, the sheer rigor involved.
It really is a testament to persistence, isn't it? And that
Mm.
basic human curiosity.
Totally. Okay, so let's start at the beginning, or maybe way back.
Way back, yeah.
Because this quest to understand light and matter, it's ancient. You find hints in texts like Mo Tzu from, 4th century BC China.
It's amazing how long we've been asking these questions.
And then you jump forward. Roentgen discovering X-rays in 1901, the first physics Nobel. It's this long, continuous thread.
And the 20th century just pulled that thread so much tighter with theory. I mean, you had Dirac suggesting light could create matter-antimatter pairs.
Electrons and positrons, just like appearing from energy. Mind-blowing.
Totally. Then Lamb and Rutherford mapping out the details of how photons and electrons interact, all leading up to quantum electrodynamics, QED.
Our rulebook for light and matter.
Pretty much, yeah. Formulated by giants like Tominaga, Schwinger, Feynman, Weisskopf. It was a revolution in understanding.
And it's fascinating how this grand theory connects to Ting's own journey. He talks about reading Herzberg's atomic spectra back in '57, shaping his view of light quanta.
And that QED textbook his father gave him for Christmas?
Right. A Kaiser and Berestetsky. He apparently worked through the formulas himself. He was also really into Drell's work on testing QED at short distances, even did some theory with Brodsky.
See, these aren't just like background details. This deep dive into theory, his personal drive, it all fed directly into his vision for experiments. He wasn't just learning, he was thinking, what's next?
Which led him towards looking for these heavy photons.
Exactly. Vector mesons, basically heavier versions of the photon that might also carry forces. It was the next logical step, fueled by that deep QED understanding.
Okay, so testing QED itself, there wasn't just one way to do it.
No, not at all. There were really two main paths people were taking. The first was low-energy experiments. Super precise.
Designed for incredible accuracy, right?
Ugh.
Checking the theory's predictions down to the decimal points.
Precisely. A classic example is the muon G2 experiment. At CERN, Picasso's group, around 1975.
Yes, I remember that one. The precision was legendary.
It really was. They measured the muon's magnetic properties to 10 parts per million, and guess what?
It matched QED.
Perfectly. I mean, the agreement between the experiment and the theory was it was stunning. A fantastic achievement, really, for both sides.
Okay, so that's locking down the known theory. What was the other path?
The other path was more, exploratory. High-energy experiments.
Pushing the boundaries.
Exactly. Less about pinpoint accuracy on known predictions, and more about probing QED where it hadn't really been tested at really short distances.
Which ties into the uncertainty principle, right? Higher energy lets you see smaller stuff.
You got it. But this approach, it came with huge challenges. Trying to create electron-positron pairs with high-energy photons, for instance.
It's rare, right?
Incredibly rare. It's what physicists call third order in alpha, meaning it just doesn't happen very often. So you need, two things. A ridiculously intense incoming beam.
And massive detectors. Huge acceptance to catch anything you could.
Exactly. Like trying to catch raindrops in a thimble versus a giant bucket.
So you have these two approaches. One confirming known territory with extreme precision, the other pushing into the unknown, maybe less precisely, but looking for something new.
And both are absolutely crucial. You need both to really advance our understanding. They work together.
Okay, let's get practical. How do you actually detect a particle that might vanish almost instantly?
The key concept there is effective mass.
Right. If something decays into two other particles.
By measuring the momentum and the angles of those two outgoing particles very, very precisely, you can essentially reconstruct the mass of the original short-lived parent particle, even though you never saw it directly.
So you need a tool to do that measurement.
And that's the pair spectrometer. Think of it like a detector with two arms. Each arm measures the momentum and angle of one of the outgoing particles.
And by tuning what momenta you accept.
You can effectively scan through different possible masses for that parent particle, and if there is a new particle decaying at a specific mass, you'll see it. It pops up as a sharp peak, a narrow resonance against the smooth background.
Like a clear signal saying, I was here.
Exactly. Unmistakable.
And Ting got his grounding in this kind of work early on, right? At DEAY.
Yeah, back in Hamburg around 1965. That experience was foundational. He talks about the detector they built there for E+E production. It was really state-of-the-art for the time.
What made it special?
Well, it had to handle this immense photon beam, billions per second, but also have a large acceptance, a wide view to catch the rare events. And critically, it needed to reject other particles, hadrons.
The stuff you don't want to see.
Right. And their system was ingenious. It could reject hadrons by a factor of over 100 million, using special Cherenkov counters, shower counters, even magnets to just sweep away unwanted stuff.
Wow. 100 million to 1 rejection. That's hard to grasp.
It really is. And the dedication required. Ting mentions event rates were sometimes just 1 per day, sometimes no events for days.
Ugh, that must have been tough.
Absolutely. So they developed these incredibly strict procedures, manually checking all the voltages every half hour, calibrating the whole spectrometer every single day.
No switching things off.
Never. Physicists stayed on shift even when the accelerator was down for maintenance. They even built a special grounding system just for their electronics to avoid noise. It was obsessive, almost.
But that rigor paid off.
It did. It gave them a mass resolution of about 5 MeV, which was sharp enough to clearly see known narrow particles like the Rho and omega mesons. It proved the technique worked.
And even that early DE-SWI work was hinting at bigger things.
Yeah, it supported the idea of quarks as fundamental building blocks, and this concept of vector mesons, these heavy photons, being mediators of the electromagnetic force. The groundwork was definitely laid.
Okay, so building on that DE-SWI experience, Ting starts thinking bigger.
Right. He asked this really fundamental question. We know photons can turn into these heavy photons like Rho, omega, phi, all around 1 GeV mass. Why only 3?
Shouldn't there be more?
Exactly. Why should nature stop there? That curiosity, that question, drove him to propose a new experiment to search for heavier ones, up to maybe 5 GeV.
And for this bigger hunt, he chose Brookhaven National Lab.
He did in 1971. It was a strategic choice. Brookhaven had a powerful 30 GeV proton accelerator.
Why protons? Why not photons again, or one of those electron-positron colliders?
Good question. For a search, he figured proton-proton collisions would be better. You smash protons together, you get a whole mess of particles, a higher production rate for new things like vector mesons via the strong force. It's messy, but good for finding something unknown.
More chances to produce something new.
Exactly. Plus, you could get a high-intensity, high-duty cycle beam. Electron-positron rings are great for studying a particle. Once you know it's there, you can tune the energy precisely. But for just looking across a wide mass range, the proton beam seemed better for a systematic search.
Makes sense.
Yeah.
So what did the experiment actually need to do? The requirements must have been intense.
Oh, absolutely. First, detect narrow particles over that wide mass range, up to 5 GeV. Handle a proton beam intensity of maybe 10,012 protons per second.
Huge intensity.
Huge. And again, that phenomenal hadron rejection, better than 100 million to 1, because the electron-positron signal they wanted was still tiny compared to everything else.
And placement mattered too.
Critically, they calculated the optimal angle for the decay products to emerge 14.6 degrees. Interestingly, independent of the mass of the new particle they were looking for, every detail was considered.
That's incredible foresight.
They even designed the beamline itself meticulously. Following advice from CERN's Dr. Diddins, they used only magnets to focus the beam, no collimators to keep it clean and reduce background noise. Constant monitoring of beam intensity, stability, daily calibrations. Nothing left to chance.
Okay, let's picture this machine. The double-arm spectrometer at Brookhaven. You said it built on the DSWA experience.
Very much so. It was designed specifically for high-intensity, large mass acceptance, and good mass resolution. A real beast, but a precise one.
So break it down for us. What were the key parts?
All right, first, the target. It wasn't just one lump. It was 9 thin slices of beryllium spaced apart.
Why spaced out?
Super clever reason. It helped them figure out where the particle pair came from. If the tracks pointed back to the same thin slice, it was likely a real event. If they came from different slices, probably just accidental junk. Helped reject background.
Smart. Okay, what else? Magnets.
Oh yeah, big dipole magnets. M0, M1, M2, powerful. They bent the particles, crucially, so the detectors didn't look directly at the target, cutting down noise enormously. And the field. Mapped at 100,000 points for precision.
Wow. And the detectors themselves. The chambers.
Those were cutting edge. Multi-wire proportional chambers, get this, over 8,000 incredibly fine gold-plated wires, just 20 microns thick.
Tiny wire.
Tiny. And they did this neat trick. Rotating the wire planes by 60 degrees in some chambers, that helps sort out events with multiple particles, multiple tracks, and reject stray neutrons or gamma rays.
How fast could they operate?
Really fast, around 20 millihertz.
Yeah.
They could handle up to 8 particles per arm. And these chambers were key to getting that MIC-5 MeV mass resolution and the ability to scan a 2GeV mass range simultaneously. But fixing even one broken wire meant moving nearly 1,000 tons of concrete shielding.
No pressure.
Yeah.
Okay, magnets, chambers. What about identifying the particles, making sure they were electrons?
That's where the Cherenkov and shower counters came in. They were the final piece for getting that incredible 108 hadron rejection, designed to minimize scattering using special mirrors, highly sensitive phototubes that could see just a few photons of light, even from helium gas.
Everything optimized.
Everything. And there was another counter, CB, right near the target, specifically good at rejecting pions but seeing electrons, used for calibration and triggering the whole system.
And you mentioned this p-theta independent idea.
Yeah, that was elegant. Momentum was measured by the vertical bend from the magnets, while the production angle was measured horizontally. Separating those measurements simplified the analysis and boosted the resolution.
It's just the sheer scale and the meticulous detail is staggering.
It really is. It shows you what it takes, pushing the absolute limits of engineering and ingenuity just to catch these tiny, fleeting glimpses of reality.
But building and running this wasn't exactly easy, right? There were hurdles.
Oh, big time. Ting faced a lot of criticism beforehand. He mentions one prominent physicist basically saying, that spectrometer is only good for finding narrow resonances, and there are no narrow resonances.
Ouch. What did Ting do?
He trusted his gut, his experimental intuition, more than the theoretical arguments at that point. He just decided to push ahead with the design.
Gutsy. But then things got genuinely scary.
Yeah, the radiation scare in April '74. That sounds terrifying. Control room alarms going off, radiation levels so high the team would hit their yearly limit in just 24 hours.
What was causing it?
It took some searching, but Dr. Becker found it. Despite literally 10,000 tons of concrete shielding blocks everywhere else, the very top of the main beam stopper, completely unshielded, a critical oversight.
Unbelievable. Did they fix it quickly?
Very quickly. Once they plugged that gap, the levels dropped and they could get back to work, thankfully.
It really highlights the risks, and it makes their focus on checks and validation even more understandable.
Absolutely. Their rigor was just next level. They constantly mapped detector efficiencies, calibrated everything continuously, checked timings. Nothing was taken for granted.
And the analysis itself?
That was maybe the most impressive part. Ting insisted on having 2 independent teams analyze everything.
2 teams doing the same work?
Yep. 2 sets of Monte Carlo simulations, 2 sets of event reconstruction, 2 sets of corrections, 2 final sets of results, and they had to agree.
That must have doubled their computing time.
It did, but it built immense confidence. If 2 separate analyses came up with the same answer, you could really trust it. Plus, they did tons of specific background checks, varying the beam intensity, checking the target thickness dependence to rule out any possibility of a fake signal.
So this wasn't just careful science. This was like bulletproofing their results against any possible doubt.
Exactly. It was conviction, an absolute commitment to ensuring that if they did find something, it was undeniably real.
Okay, so picture this. It's late August 1974. Years of design, building, debugging, checking. The spectrometer magnets are finally said to scan the mass range from 2.5 up to 4.0 GeV. What happened?
Ting describes it with real excitement. He says, immediately we saw clean, real electron pairs. After all that searching, there they were.
Wow. And was it just a few pairs or something more?
Something much more. The data was incredibly clear. Most of the pairs weren't spread out randomly. They clustered, forming a sharp, narrow peak right at an energy of 3.1 GeV. The width was less than 5 MeV, the signature of a new particle.
The resonance they've been hunting for.
Precisely. But they had to be sure, so they did a crucial check. They deliberately changed the magnet current slightly. If it was an instrumental effect, the peak's apparent energy might shift.
But it didn't.
It stayed locked solid at 3.1 GeV. That was the clincher. It proved it wasn't an artifact. It was a real particle they discovered.
The eureka moment.
Okay.
Incredible. And the name. J particle. Why J?
King had a couple of reasons. He wanted to use Roman letters for what he felt were really exciting, stable-ish particles, like the theoretical W and Z bosons, distinguishing them from particles with Greek letter names. And the letter J also looks a bit like the Chinese character for his name, plus it relates to the electromagnetic current, often written as Ju, which they were studying.
Multiple layers there. Okay, so they found it,
hmm
but then things got complicated, the publication.
Yeah, it led to this famous simultaneous discovery situation. Ting found the J particle, and he informed the Adone storage ring group at Frascati in Italy on November 11th.
And they saw it too.
By November 15th, yes. They tuned their machine and saw the signal as well. Both groups rushed to publish, and their papers actually appeared in the very same issue of Physical Review Letters.
Wow. Talk about confirmation.
Exactly. And Frascati's later, more detailed studies nailed down just how weirdly long-lived this particle was. Its width was only about 60 keV. That meant it lived about 1,000 times longer than similar particles like the Romanzon. It was truly different.
So two different labs using totally different techniques. Protons hitting a target versus electron-positron collisions find the same thing almost at the same time.
It's a beautiful example of how science works, right?
Yeah.
That independent confirmation gives you enormous confidence that you found something real and fundamental, a monumental discovery validated almost instantly.
And finding J wasn't really the end of the story, was it? It was more like cracking open a door.
Oh, absolutely. It triggered a whole cascade of new discoveries, an explosion of research, really.
What came next?
Well, almost immediately, a related particle, a sister state called the psi prime, was found at SLAC, the Stanford Linear Accelerator Center.
So another one, slightly heavier.
Yep. And suddenly, those electron-positron storage rings, like the ones at SLAC in Frascati and also DSEIY in Germany, became the perfect tools. They weren't great for the initial search, but for studying these new particles, they were ideal. Because you could tune the collider energy precisely to the mass of the J or the S and just produce them like crazy. The production rate went up by more than a factor of 100 compared to Ting's experiment. They became J factories.
Allowing for much more detailed study.
Exactly. Groups like DESP at DDY started seeing complex decay chains, like the S decaying, emitting a photon, turning into another intermediate particle, which then decayed into the J with another photon. Things got intricate fast.
And what did this all mean for the bigger picture? For quarks?
That was the huge theoretical impact. The existence of the J, especially its properties, just didn't fit the existing picture with only 3 quarks. Up, down, strange. It basically demanded the existence of a 4th quark, the charm quark.
Which theorists like Glashow had predicted.
Exactly. It was stunning confirmation for the quark model, but a significantly expanded version of it. It really shifted the paradigm. And it didn't stop there. Soon, more experiments at Brookhaven, DESY, Fermilab, SLAC started finding evidence for even more related states, particles containing this new charm quark. It cemented this whole new layer of understanding about matter's fundamental constituents.
So when you, the listener, think about this, realize that one discovery, achieved through incredible effort and rigor, didn't just add a particle, it opened up a whole new chapter in physics, confirmed the existence of a new fundamental building block of the universe, and reshaped our entire understanding of reality. It's pretty profound stuff.
Absolutely profound.
So our deep dive today took us from ancient questions about light all the way to this incredibly meticulous, high-stakes search for the J particle by Samuel Ting and his team. We've seen the ingenuity, the challenges, the confirmation, and the revolutionary impact it had.
Yeah, changing our view of quarks, the fundamental forces, it was huge.
And what's really striking is that even back in 1976, right after the discovery, Ting was already asking the next big questions, questions that still drive physics today.
Right. He was wondering, what other photon-like particles might be out there at even higher energies. How many more quarks are there? We now know of 6, but are there more?
And that fundamental puzzle. If quarks are real fundamental things, why haven't we ever seen one just floating around on its own?
Exactly. Why are they always confined inside other particles? These are the frontiers particle physics is still exploring, building on the legacy of discoveries like the J.
Which leaves us with maybe a final thought to chew on. The J particle story is a powerful reminder. Even when the leading theories, even eminent scientists say there's nothing there sometimes. Well, sometimes persistence, ingenuity, and trusting the experimental evidence can reveal a whole new layer of reality we never expected.
Makes you wonder what assumptions we're making today, doesn't it?
It certainly does. What might the next generation of explorers uncover? Thank you for joining us on the Deep Dive.